Hello, viewers. Today's topic for the discussion is correlation. And in this correlation, we'll be discussing about the correlation, its causation, and we'll all be talking about correlation versus causation and the correlation coefficient. So the first question that I will be asking you, do you have the understanding of what is correlation? If yes, it's okay, it will help you. Otherwise, let me tell you what is correlation. So, correlation is a statistical measure that expresses the extent to which two variables, let's say x and y, are linearly related. That means they change together at a constant rate. If there is a change in one, there will be change in another. Now, this change can be positive also and negative also. So this correlation can be called as a common tool for describing simple relationship without making a statement about the cause and effect. Now, another question that arises to our mind is how is this correlation measured? So this correlation, we have correlation coefficient that is called as R, and this quantifies the strength of the relationship between the two variables, let's say x and y, and the correlations are also tested for their statistical significance. Now, another question that you can ask to me is what are the limitations of this correlation analysis? Correlation actually can't look at the presence or effect of other variables outside of the two being which are being explored. Okay, so there may be the change may be because of the other. Okay, so that is not, it is not able to identify. And importantly, correlation doesn't tell us about the cause and the effect. So correlation also cannot accurately describe curvilinear relationships. So then what are the correlation then describes? So correlations basically describe the data which is moving together. So in other words, we can say correlations are useful for describing simple relationship among the data. For example, let's imagine that we are looking at a data set of a campsites in a mountain park. Now we want to know whether there is a relationship between the elevation of the campsite, that means how high the mountain it is, and the average high temperature in the summer. So for each individual campsite, we have to measure two things. One is the elevation and the other is the temperature. So when we compare the two variables across the sample with a correlation, we can find that there is a linear relationship. That is, as the elevation increases, the temperature drops. So we can say that the elevation and the temperature are negatively correlated. So what do the correlation number mean? We describe correlations with the unit-free measure called the coefficient of correlation, or we can say correlation coefficient. This ranges from -1 to +1 and is denoted by R. The statistical significance is indicated with the p-value. Therefore, correlations are typically written with the two key numbers, that is R and P. Now, closer R is to 0, the weaker the linear relationship is. Positive R values indicate a positive correlation, whereas the values of both variables tend to increase together. Now, negative R values indicate a negative correlation, and here the values of one variable tend to increase when the values of the other variable decreases. The p-value gives us evidence that we can meaningfully conclude that the population correlation coefficient is likely different from 0. So based on what we observe from the sample. Now unit-free measure, that means the correlation exists on their own scale. So in our example, the number given for R is not on the same scale as either elevation or temperature. So this is different from other summary statistics. For instance, the mean of the elevation measurement is on the same scale as its variable. So now another question arises. What is then p-value? A p-value is a measure of probability used for hypothesis testing. Now, this p indicates the likelihood of obtaining the data that we are seeing if there is no effect present. In other words, in case of the null hypothesis, for example, the campsite data which we have taken, now this would be the hypothesis that there is no linear relationship between elevation and temperature. When a p-value is used to describe a result as statistically significant, this means that it falls below a predefined cutoff. That means our p-value can range, it can be less than 0.01 or it can be less than 0.015. So at which point we reject the null hypothesis in favor of an alternative hypothesis, which here we can take it as our campsite data that there is a relationship between elevation and the temperature. And once we have obtained a significant correlation, we can also look at its strength. A perfect positive correlation has a value of 1 and a perfect negative correlation has a value of -1. But in real world, we would never expect to see a perfect correlation unless one variable is actually a proxy measure for the other. So in fact, seeing a perfect correlation number, it can be an alert to us to an error in our data. For example, if we accidentally recorded distance from sea level for each campsite instead of temperature, this would correlate perfectly with elevation. So another useful piece of information is a number of observation, that is the capital N. So as with most statistical tests, knowing the size of the sample help us to judge the strength of our sample and how well it represents the population. For example, if we only measured elevation and temperature for 5 campsites, but the park has 2000 campsites, then we had want to add more campsites to our sample. Now, same thing, that is the correlation can be also visualized with scatter plots. So let's see visualizing correlations with scatter plots. Now back to our example of the campsite. As campsite elevation increases, the temperature drops. That was our conclusion. So we can look at this directly with the scatter plot also. Imagine that we have plotted our campsite data. That is, each point in the plot represents one campsite, which we can place it on the x-axis and y-axis by its elevation, and summertime we can say the high temperature. So the correlation coefficient R, that is which illustrates our scatter plot, it tells us in numerical terms how close the points mapped in the scatter plot come to a linear relationship. Now, stronger is the relationship, or let's say bigger is the R value, means relationships where the points are very close to the line and which we have fit to the data. So as you can see in this diagram, we have elevation in feet and summer high temperature in Fahrenheit. And here you can say the height and the temperature has been plotted for the various campsites. And we can see uh, there is a linear relationship as when we join some of the points and it is forming a linear line. So here we can have some more complex relationship also. So like scatter plots we have seen are also useful for determining whether there is anything in our data that might disrupt an accurate correlation, such as unusual patterns like curvilinear relationship or an extreme outlier. Correlations can't accurately capture curvilinear relationships. So in a curvilinear relationship, variables are correlated in a given direction until a certain point, and where the relationship then changes from that point onwards. For example, Imagine that we looked at our campsite elevations and how highly campsite rate each campsite. So on an average. Now, perhaps at first, elevation and campsite rankings are positively correlated because higher campsites get better views of the park. But at a certain point, higher elevations become negatively correlated with the campsite rankings because campers feel cold at night. So, looking at this graph, we can see elevation and the rating. And rating is on a point of 1 to 10 scale. And so, in the beginning, if you see, as the elevation is rising, people are giving good rating, but beyond a certain elevation, we are seeing that the ranking is going down. So here we can get even more insight by adding shaded density ellipses to our scatter plots. A density ellipse illustrates the densest region of the points in the scatter plot, which in turn help us to see the strength and direction of the correlation. Now, density ellipses can be of various sizes. One common choice for examining correlation is 95% density ellipse, which captures approximately the densest 95% of the observations. If two variables are moving together, like our campsite's elevation and temperature, we would expect to see that this density ellipse mirror in the shape of the line. Okay, so we can see that in a curvilinear relationship, the density ellipse looks round. Correlation won't give us a meaningful description of this. Let's understand this density eclipses with the diagram. Okay, so here we can see we have the first density eclipse. As you can see, elevation versus summer high temperature Fahrenheit, and here the you can see the densest part. Okay, and in the second graph you can see the elevation and the rating. So here also we can see the where is the densest rating of this campsites. So we can from the graph also we can find out whether what shape is being taken by the data. So whether it is linear, whether it is curvilinear, or it is making a circle, or it is making, so whatever is the shape, accordingly we can draw our conclusions. Now let's understand the coefficient correlation, or we call it as correlation coefficient. So what is correlation coefficient? The correlation coefficient is the specific measure that quantifies the strength of the linear relationship between two variables in a correlation analysis. The correlation coefficient is what we symbolize with the R in a correlation report. Then how is the correlation coefficient used? That can be one question in your mind now. So for two variables, the formula compares the distance of each data point from the variable mean and uses this to tell us how closely the relationship between the variables can be fit to an imaginary line drawn through the data. This is what we mean when we say that correlations look at linear relationships. So what are some limitations of coefficient of correlation? Obviously, there are some. So correlation only looks at the two variables at hand and won't give insight into relationship beyond the bivariate data. So this test won't detect and therefore will be skewed by if there are outliers in the data, and it can't properly detect curvilinear relationship. So another question that comes to our mind is, what do the values of the correlation coefficient mean? What does the R means? The coefficient correlation R is a unit free value, as I have already told you in my previous slides, and the value lies between -1 and +1. The statistical significance is indicated with a p-value. Therefore, correlation are typically written with two key numbers, that is R and P. So R is closer to 0, weaker the relationship, and positive R values indicate positive correlation, where the values of both variables tend to increase together. The negative R values indicate a negative correlation, where the values of one variable tend to decrease with the values of the other variable. Now, the values 1 and -1 both represent perfect correlation. So, positive and negative respectively, depending on the sign. Two perfectly correlated variables change together at a fixed rate. So, we say that they have a linear relationship. When plotted on a scatter plot, all data points can be connected with a straight line. The p-value also helps us to determine whether or not we can meaningfully conclude that the population correlation coefficient is different from zero. So based on what we observe from the sample. P-value and R-value can be used interchangeably also. A p-value is a measure of probability for hypothesis testing. The goal of the hypothesis testing is to determine whether there is enough evidence to support a certain hypothesis about the data which we are referring to. So actually we formulate two hypotheses, the null hypothesis and the alternate hypothesis. Like in the case of correlation analysis, the null hypothesis is typically that the observed relationship between the variables is the result of pure chance. That means the correlation coefficient is really zero and there is no linear relationship. The alternative hypothesis is that the correlation we have measured is legitimately present in our data. That means the correlation coefficient is different from zero. So the p-value is the probability of observing a non-zero correlation coefficient in our sample data, when in fact the null hypothesis is true. So a low p-value would lead to the reject of the null hypothesis. Now, a typical threshold for rejection of the null hypothesis is a p-value of 0.05. That is, if we have a p-value less than 0.05, we would reject the null hypothesis in favor of the alternative hypothesis. That means the correlation coefficient is different from zero. So how do we actually calculate the coefficient correlation? So here we have the sample correlation coefficient and this is the formula given on the slide. R is equal to summation xi minus x bar into yi minus y bar divided by under root summation xi minus x bar whole square into summation yi minus y bar whole square. So here we can understand R is the sample correlation coefficient, summation sign which we use, so that is there, okay, and xi is the value of the x and x bar is the mean of the x variable. Same way yi is the value of y and y bar is the mean of the y variable. And here we can see this whole summation xi minus x bar whole square. This is the sum of the square deviation for x. And similarly, we have the sum of the square deviation of y. So let's understand this through a small step and to calculate the correlation coefficient. And here I'm going to give you a small set of simple numbers so that it is easy to follow the operations. Okay. So let's imagine that we are interested in whether we can expect that there will be more ice cream sales in our city on hotter days. So ice cream shops start to open in the spring. Perhaps people buy more ice cream on days when it's hot outside. So on the other hand, perhaps people simply buy ice cream at a steady rate because they like it so much. So now we start to answer this question by gathering data on average ice creams sales per day and the highest daily temperature. So ice cream sales and the temperature are now the two variables which we'll use to calculate the correlation coefficient. Now sometimes the data like these are called as bivariate data because each observation or a point in time at which we have measured both sales and temperature has two pieces of information that we can use to describe it. In other words, we are asking whether ice cream sales and temperature seem to move together or not. So here through the graph, you can see temperature and the ice cream sales. Okay, so we have plotted for three different, you can say, temperatures and we got three different numbers for the ice cream that is sold. So we can look at this data, and where ice cream sale is 3, so temperature was 70 degree Fahrenheit. When ice cream sale was 6, it was 75 degree Fahrenheit. And when it was 9, it was 80 degree Fahrenheit. So we can also look at this data in a table, as I have already told you, which is very handy for helping us to follow that the coefficient calculation for each data point. So when talking about this bivariate data, it's typical to call one variable x and the other variable y. So these also help us to orient ourselves on a visual plane, such as x-axis of a plot. Let's call that ice cream sales is x and temperature is y. So here we note that each data point is paired. Remember, we are really looking at individual points in time. So each time has a value for both sales and temperature. So here x bar is equal to values of the ice creams, that is 3 plus 6 plus 9. So total divided by 3. So mean comes to 9 plus 6 is 15. 15 plus 3 is 18. 18 divided by 3 is 6. Similarly, we can take it for y. Y bar is equal to sum of the all the three temperatures, that is 70 plus 75 plus 80, and divided by 3. So it comes to 75. Okay, so this was the first step which we have done, finding the sample means. So here we can see the x bar value is 6 and y bar value is 75. Now, second step, we will calculate the distance of each data point from its mean. So when we calculate the distance, that is xi minus x bar. So taking the first data point, that is 3, and the mean value is 6. So 3 minus 6 is minus 3. 6 minus 6 is 0 and 9 minus 6 is 3. Similarly, we do it for the y, that is yi minus y bar. So first value of the temperature is 70. 70 minus 75. 75 is the average or mean temperature. So we got minus 5. Then 75 minus 75 is 0 and 80 minus 75 is 5. So this way we have to calculate the second step. That means we have found the distance of each data point from its mean. Okay, and we note that this operation sometimes results in a negative number or 0 also. Okay, so coming to the third step, that is we will complete the top of the coefficient equation. So we have already done summation xi minus x bar into summation yi minus y bar. So it is minus 3, okay, into minus 5 plus 0 into 0 plus 3 into 5. So that comes to 30. Okay, so xi minus x bar in the first step, if you see, is minus 3, and similarly for y it is minus 5. So minus 5 into 3 is, it is 15. Then second point it's 0 0, and third point is again 3 and 15. So 15 plus 15 is 30. So this is what we have calculated, the numerator value of our equation of the correlation coefficient. So we have taken the paired values for each row, and then we have calculated and summed up, and the result is 30. Now, what is the insight that we get from this? So we see that the sum of the products calculation and the location of the data points in our scatter plot are intrinsically related. So sum of the products is positive for our data when the sum of the products, that is numerator of our correlation coefficient, is positive. So the correlation coefficient R will be positive, since the denominator is the square root, will always be positive. So we know that the positive correlation means that increases in one variable are associated with the increases in the other, like our ice cream sales and the temperature. So when we see it on the scatter plot also, we can see that the data points angle upwards from left to right. So how we can say that this is a linear relation and it is moving from it is moving in the positive direction. That means the relationship is positive. So the only way we will get a positive value for the sum of the products is if the products we are summing tend to be positive. And the only way to get a positive value for each of the products is if both values are negative or both values are positive. So the only way to get a pair of two negative numbers is if both values are below their means. On the bottom left side of the scatter plot, we can see that. And the only way to get a pair of two positive numbers is if both values are above their means. Okay, so the sum of the products tells us whether data tend to appear in the bottom left or top right of the scatter plot. That means a positive correlation. Or alternatively, if the data tends to be appear in the top left and bottom of the right of the scatter plot, that means it is a negative correlation. So here we can see mean of x and mean of y, and we can see where it is, whether it is positive, negative. So likewise, I was telling you, right, left, all these you can see over here. Okay, so now coming to the fourth step, that is, we will complete the bottom of the coefficient equation. So bottom, that means denominator of our coefficient equation is summation xi minus x bar whole square into summation yi minus y bar whole square under root. So here xi minus x bar we have seen minus 3 plus square of it, then 0 square of it, and 3 square of it, so it comes to 18. Similarly, for y it comes to be 25 plus 0 plus 25, so it comes to be 50. Now multiplying both, so 18 into 50 is 90018. Okay, and into this 9. Okay, so we get how much? 900. So under root of this is 30. So this is what is you can say the denominator value. So now as we have already calculated the numerator was 30 and denominator is also 30. So we can compare this with the scatter plot also. It is coming to be, as you can see, I can see tell you, this is what is our scatter plot. If we join it is a straight line, so it shows perfect combination. So now as we can see, R is 1. So this shows perfect correlation between ice cream sales and hot summer days. So of course, finding a perfect correlation is so unlikely in the real world that we had been working with real data. So we had assumed that we had done something wrong to obtain such a result. But this result from the simplified data in our example should make intuitive sense based on simply looking at the data points. Let's look again at our scatter plot. So now imagine drawing a line through that scatter plot. Now, would it look like a perfect linear fit? Yes or no? Okay, so picture can be a worth 1000 correlation coefficients. So scatter plots and other data visualizations, they are very useful tools throughout the whole statistical process, not just before we perform our hypothesis testing. So it's important to remember that relying exclusively on the correlation coefficient can be misleading. So particularly in situations involving curvilinear relationships or extreme outliers. So in the scatter plot, we are reminded that a correlation coefficient of 0 or near to 0 does not necessarily mean that there is no relationship between the variables. It simply means that there is no linear relationship. So here you can see various different types of scatter plots. We can have insight from all these on how outliers, that is what is our unusual observation in our data, which can skew the correlation coefficient. Okay, so here we can see from here, like this is curvilinear and these 2 points are outliers. And similarly here, this is the outlier. There are so many outliers, some values which are extremely So this is what is our curvilinear relationship. This is cyclic relationship. And here you can see correlation. It's so difficult to draw any diagram. So curvilinear relationship is not there. Okay. But still we can draw something like this. Similarly here we can see it is giving us as like cyclic. Okay. So correlation, this is not correct ones. Okay, this if this such type of diagrams are there, then we can simply say that correlation coefficient indicates that there is not strong positive relationship. Okay, but once the outliers are removed, the correlation coefficient may be nearly to zero. There is relation. If we remove these outliers, then we can simply draw something, okay, some sort of relationship. So here we can see R is equal to, again we have done through density eclipses. Okay, so where this is an outlier, as you can see. uh, Okay, if there are outliers in our data set, then we really need to be worried about whether our data set is right or wrong. Okay, whether we are on the right path, right, this thing or not. Okay, so next is correlation versus causation. We need to understand correlation test for a relationship between two variables. So whether one is causing the other or not, or where is the center of causation. So seeing two variables moving together does not necessarily mean we know whether one variable causes to the other to occur. So this is why we commonly say that correlation does not simply causation imply to the causation. A strong correlation might indicate causality, but there could easily be other explanations also. It may be the result of the random chance, where the variables appear to be related, but there is no true underlying relationship. There may be a third or lurking variable that makes the relationship appear stronger or weaker, as the case may be, than it actually looks. So, for observational data, correlations can't confirm the causation. Similarly, correlations between variables show us that there is a pattern in the data, that the variables we have tend to move together. However, correlations alone don't show us whether or not that the data are moving together because one variable causes the other. So it's possible to find a statistically significant and reliable correlation for two variables that are actually not causally linked at all. So in fact, such correlations are common, and often this is because both variables are associated with a different causal variable, which tends to co-occur with the data that we are measuring. Let's do a small example exercise. Okay. So let's think about with an example and imagine that you are working at health data and you observe statistically significant positive correlation between exercise and the cases of the skin cancer. That is, the people who exercise more tend to be people who get skin cancer. This correlation seems strong and reliable and shows up that across multiple populations of patients. Without exploring further, you might conclude that exercise somehow causes cancer. Now, based on these findings, you might even develop a plausible hypothesis. That is, perhaps the stress from exercise causes the body to lose some ability to protect against sun damage. But imagine that in reality, this correlation exists in your data set because people who live in places that get a lot of sunlight year round are significantly more active in their daily lives than people who live in places that don't have the enough sunlight. So this shows up in the data as increased exercises, and at the same time, increased daily sunlight exposure means that are more cases of skin cancer. Now, both the variables, rate of the exercise and the skin cancer, they were affected by a third causal variable, that is exposure to the sunlight, but they were not causally related. So, but when with well-designed empirical research, we can't establish causation. So, distinguishing what does or does not provide causal evidence is a key piece of the data literacy. Now, determining causality is never perfect in real world. So, however, there are a variety of experimental, statistical, and research design techniques for finding evidence towards causal relationship. Examples are randomization, controlled experiments, predictive models with multiple variables, and beyond the intrinsic limitations of correlation test, that is, correlations cannot measure trivariate and potentially causal relationships. So it's important to understand that evidence for causation typically comes not from individual statistical tests but from careful experimental design. Let's take one more example before we conclude our topic. Let's take an example like imagine that we are health researchers, and this time we are looking at a larger data set of disease rates, diet, and other health behaviors. So suppose that we find two correlations. Increased heart disease is correlated with the higher fat diets. That is a positive correlation, and increased exercise is correlated with less heart disease. That is a negative correlation. So both of these correlations are large and we find them reliably. So surely this provides a clue to causation, right? Okay, let's see it. So in the case of this health data, correlation might suggest an underlying causal relationship, but without further work, it does not establish it. Imagine that after finding these correlations, as a next step, we redesign a biological study which examines the ways that the body absorbs fat and how this impacts the heart. Perhaps we find a mechanism through which higher fat consumption is stored in a way that leads to a specific strain on the heart. We might also take a closer look at exercise and design a randomized controlled experiment which finds that exercise interrupts the storage of the fat, thereby leading to less strain to the heart. Now, all these pieces of evidence they fit together into an explanation. Higher fat diets can indeed cause heart disease, and the original correlations still stood as we dove deeper into the problem that high fat diets and heart disease are linked. Now, in this example, we notice that our causal evidence was not provided by the correlation test itself, which simply examines the relationship between the observational data, such as rates of heart disease, and reported diet and exercises. Now, instead, we used an empirical research investigation to find evidence for this association. So, we need to explore the causation. What right kind of investigation should we do in order to explore the causation? Now, understanding causation is a difficult problem. It is not so easy. Okay, so in the real world, it's never the case that we have access to all the data, that we might need to map every possible relationship between variables. But there are some key strategies to help us isolate and explore the mechanisms. So we'll see that, for example, in a controlled experiment, we can try to carefully match two groups and randomly apply a treatment or intervention to only one of the groups. So this is what is, we can say, a principle of randomization. It is a key in experimental design, and understanding this context can change what we are able to infer from statistical tests. Let's think again about the first example before we conclude, that examined the relationship between the exercise and the skin cancer rates. Imagine that we are somehow able to take a large, globally distributed sample of people and randomly assign them to exercise at different levels every week for 10 years. At the end of that time, we also get the skin cancer rates for this large group. So we will end up with a data set which has been experimentally designed to test the relationship between exercise and skin cancer. So because exercise was directly manipulated in the experiment via random assignment, it will not be systematically related to any other variables that could be different between these two groups, assuming all other aspects of the study are valid. This means that in this case, because our data was derived via sound experimental design, a positive correlation between exercise and skin cancer would be meaningful evidence for causality. Okay, learners, so I hope you understood the basics of the correlation, and thanks for your patience listening. We'll meet again with a new topic in the next session. Have a good day.